In this tutorial, we will compare simulation and real-time measurements in TINA. Let's first open a circuit in the Examples Measurement folder. We open the RLC circuit and zoom in on it. Next, we carry out a transient analysis from the Analysis menu. Select Transient and the Transient dialog appears. Press the OK button. We see the circuit response to a square wave excitation. Now, let's examine the same circuit using TINA's virtual oscilloscope. This time, we will carry out the real measurement. This is possible because the circuit is connected to the TINLab II PC oscilloscope and generator. In this way, we can carry out real-time measurements on it. The circuit and the TINLab II PC instrument as they appear in reality are visible through the camera window on the right. Now press the Run button on the oscilloscope. What you see now is the real circuit's response to the square wave excitation. If we pull the excitation out of the generator, the response will disappear. The response reappears when we plug it back into the generator. Now let's stop the oscilloscope and place this curve into a diagram window, so we can see the result of the measurement. We can change the color of the graph to lime green in order to compare it with the simulation result. Now, we can copy the curve onto the clipboard. Then, paste it onto the screen containing the simulation result. Now we are able to easily compare the two curves on the same window. We see that there is an excellent agreement at the second and third pulses of the response and beyond. There is a discrepancy, however, at the initial segment. Let's analyze this by zooming in on the curve. We see that the simulation starts from 0. The measurement, however, began after thousands of periods had already been completed. Naturally, there is a difference in the initial section. Note that with another method of measurement, the so-called transient recording, it is possible to reconcile even these initial sections. Transient recording is demonstrated in another tutorial. To finish this part of the comparison, let's add labels to the measurements. We can add a text to the drawing and even connect the label to the curve. This is an excellent way to document the simulation and measurement curves. Now let's examine the same RLC circuit in the frequency domain. First, we carry out an AC transfer characteristic analysis. We select the item from the AC menu. In addition to the amplitude and phase Bode diagram, we enable separate amplitude and phase diagrams and press OK. First, the amplitude characteristic appears. The program also generates the phase and the complete Bode diagram. Let's go back to the amplitude characteristics and measure the same characteristics using the TINLab signal analyzer instrument. We select the instrument and, due to the system's automatic synchronization, we only have to press start and the measurement begins. This measurement is much more complex than the previous domain measurements with the oscilloscope. The program needs to generate sinusoidal excitations point by point, connect it with the circuit, and wait while the stationary state takes place. The program then measures the circuit response, carries out a Fourier analysis, and draws the result point by point. In this measurement, we have 50 points, which in this case already results in a quite smooth curve. When the curve is complete, the Start button appears and we are able to export the curve into a diagram. As before, we can change the color of this measurement result curve for comparison. Before doing so, however, let's export the phase characteristics as well. This is another measurement result which has already been calculated together with the amplitude characteristics. Note that the phase characteristic measurement is quite a complicated task, but TINLab is able to handle this calculation with ease. We export the curve to a diagram and change its color to the same lime green. Finally, let's compare the simulation to the measurement. Switch to the amplitude measurement. Copy the results to the clipboard, go to the amplitude characteristic simulation, and paste them here. As we see, the results are in excellent agreement. Let's do the same with the phase measurement. Go to the phase measurement screen, copy the phase measurement onto the clipboard, then go to the phase characteristics and paste the two curves onto the same window. Again, we see an excellent agreement in the values. So far, we have simulated the circuit using numerical methods and made measurements. In addition to these methods, with TINA you can also compare the numerical simulation and the measurement with theoretical results. This can be done using TINA's unique symbolic analysis capacity. Before demonstrating this, let's first close some of the windows. Now we bring in TINA's symbolic analysis tool from the analysis menu and select AC transfer. The program will automatically generate the transfer function of this circuit using the symbolic component names. You can copy this result either into the schematic diagram using the paste icon, or bring the diagram window back from the Tools menu. Bring up the screen under the Amplitude Characteristics tab, where we have already compared the simulation and measurement curves. Now we can also add the transfer function. This feature has great educational importance, since it is possible not only to show computer simulations and measurements, but also to show how these results match with theoretical results. As in the case of this transfer function formula derived by TINA. Should you require a more detailed comparison with this formula, click on the calculator icon, which converts the formula into a program which you can execute by clicking on the green arrow button. Let's run this program. Now a complete Bode diagram is generated. You can even copy and paste these results into the previous diagram window, where we collected the simulation and measurement result. Click on this curve and copy it onto the clipboard. Click the window where we already have added the formula, the simulation, and the measurement, and add the theoretical curve. We see that it perfectly matches the numerical calculation. This concludes our demonstration of comparing simulated and real-time measurements in TINA.